Good morning. My name is Sang Bom. I am from Samsung Electronics. I am in charge of multi-core software team at Samsung Electronics. And today I'd like to talk about ZenARM status. This presentation is prepared with my colleague, engineer Jaemin Liu. And today I'd like to talk about the current ZenARM supporting hardware and software, and also I'd like to touch slightly latency issues to be improved later on for ZenARM can support real-time requirement and real-time C devices. So currently, ZenARM supports several hardware platforms, mainly ARM CPU. The current ZenARM has supported ARM V5 core, so ARM9 CPU hardware platform from Freescale i.MX21 and TI's OMAP series. And also recently, not yet released in the public domain, we ported our ZenARM to ARM11 MP core quad-core systems using ARM's RealView hardware platform. And it will be available in May, I guess. And already Goldfish Android QEMU emulator supported from last year. And in addition to that, Versatile platform board also supported. Currently, I think that Cortex-A9 core, not for multi-core, will be available also in May. The current paravirtualized operating system run on our ZenARM hypervisor is Linux 2.6.21 and 2.6.24. And in addition to that, those operating system, Micro-C OS kernel also paravirtualized. So those three operating systems have been supported since last year. New features to support multi-core ARM CPU. We added synchronization function and core topology management and vCPU migration enabled. Current ZenARM just mainly focuses on ARM V5 core. We don't have to support any multi-core issues, but we have already supported ARM11 MP core system. We enable these multi-core functions. As you can see on the screen, locking primitives are spin lock and read-write lock. Our policy is that we do not increase any locking primitives. So we would like to make our ZenARM virtually lock-free system. And to support ARM11 based on ARM v6 core, we have to support supersection of 16 megabytes sized memory mapping. So to align the 16 megabytes, we slightly changed the bootstrap procedure. At the moment, the current ZenARM is located at the lower part of system memory, taking 2 megabytes, but later on, our 2 megabytes ZenARM memory will be relocated, self-relocated during bootstrap procedure to support 16 megabyte sized memory mapping to support ARM v6 core. Let's move on to the next topic about latency analysis of ZenARM. This latency analysis is based on X-Scale hardware platform. Actually, it is made from Marvell company, and we use Linux 2.6.21. The analysis, before I'm going to talk about latency analysis, I would like to talk about background, why we are conducting latency analysis. Actually, we would like to support real-time consumer electronics devices in the future. So far, we are focusing on high throughput using ZenARM. So I believe that last year, in Shanghai, I announced that our performance in terms of RM bench, we exceed L4 microkernel. But from now on, I'd like to focus on real-time requirements, and so that our ZenARM-based system can be deployed to any real-time embedded devices. So I don't have any conclusions in this slide, but I would like to suggest we need to look at this kind of latency issues to support real-time requirements in the future based on ZenARM. We have found that worst case interrupt latency is less than around 50 microseconds. However, if there is any interrupt delivery to an active guest domain may be delayed further until the inactive domain is scheduled. And the other one is the system call latency and hypercore overhead. As you can see on the screen, the latency in the previous page less than 50 microseconds. And this page also, overhead just increased by 1 microsecond. The thing is that we do not see any large amount of latency issues in ZenARM. However, the thing is that it does not support any predictable behavior that should be supported by real-time systems. So as you can see on the screen, up to 50 microseconds in the dotted line, even though system call latency has increased by 1 microsecond, there is a vulnerable period that cannot be managed depending on application scenario. This latency will be increased by 50 microseconds. And lastly, context switching overhead. During test switching in guest domain, it is possible for ZenARM to receive any physical interrupts, even though that guest domain do not enable the interrupt. So this means that context switching overhead would be increased. According to our measurement, around 9 microseconds is collected. And the thing is that ZenARM can preempt virtual machine, but the virtual machine cannot preempt ZenARM hypervisor. That could be an issue. The thing is that if hypercore is processed, in the meantime, ZenARM receives an interrupt. So hypercore is just suspended, and the interrupt is processed. Then until our guest domain has got interrupt signaling, it has to wait another delay time. For example, suspended hypercore resumed and completed. So that kind of further delay should be sorted out to support preemptive ZenARM systems. So I think that we would like to change ZenARM structure to architecture to support real-time systems. In this picture, also has got some increased delayed time period. And this is 9 microseconds. And this is address space switching period. So TLB and cache flushing would increase delay further. Summary. Even though interrupt latency by ZenARM does not seem large, just less than 10 microseconds up to 50 microseconds, I think that we can manage it within 10 microseconds by engineering. However, event delivery to an inactive guest domain may be delayed until the domain is scheduled. That is the problem. So to support real-time C systems, we will change GenARM to be preemptible. Okay, that's it.
Anyone have any questions?
Sorry? We would like to change scheduling framework, and also we change some hypercore context as well. Sorry? No. The CPU architecture is largely different between x86 and ARM CPU. Actually, x86 based CPU has got better performance, to my knowledge, in terms of latency and other throughput. So, and also ARM CPU shows some delay in supporting virtualization functions in its architecture. For example, hypervisor mode already adopted in x86 CPU, but to my knowledge, next year or 2 years' time from now on, probably support hypervisor mode in addition to current supervisor mode and user mode. You're welcome.